matrix is not fixed. Number of columns is fixed.
In a in an organism it is also fixed. Number of rows.
Yeah, that's what I am agreeing, that in an organism it is fixed. But number of organisms at any point of time is not fixed. Okay. And generally the initial population is chosen randomly. Okay. As we mentioned that we can start with a set of initial solution, and then we will be using some kind of evolutionary procedures to obtain better and better quality solutions. So to start with, we can start with any kind of random set. Okay. So we could take into consideration the similar aspect that we normally do in other field also. Say for example, how to find out the equation of a root using Newton's-Raphson method, or by Hubble method or something like that. We start with any solution by guessing, and then in each and every iteration we try to refine the solution based on certain criteria. Here also it does the same work. Instead of working with a single solution, it tries to work with a set of solutions simultaneously, and in each and every iteration it tries to refine the quality of the solutions. Okay. So once the solutions are, once the population is obtained, initial population is obtained, the next is how do we encode the solution or decode the solution. So coding basically converts the parameter values into chromosome representation. So if x1 has been converted and used, x1 is encoded using 4 bits and x2 using 5 bits. So I need to find out ultimately what is the value of x1 and what is the value of x2. So for the, it might so happen that it's not integer, it could be continuous valued also. So for continuous value parameters, something like decimal to binary conversion should be used. So for example 13, if the string representation is 0, 1, 1, 0, 1, the corresponding integer value will be 13. And on the, for a parameter having categorical values, a particular bit position in the chromosome is set to 1 if it comes from that category. Say for example, the marital status of a person, married, unmarried, divorced, widow. So if, say for a person, the status is unmarried, then if I want to encode using 4 bits for categorical representation, the corresponding bit, the second bit, has been set to 1, rest to 0. And these strings, finally, these substrings which represent the parameters of a problem are concatenated for one complete chromosome. Decoding is the reverse of encoding. So these this particular thing, what it does, initially suppose I have this string representation. This string representation 0, 1, 1, 0, 1. So I have to find out its value, decoded value. So what will we be doing? So it's 13. 0, 1, 1, 0, 1 in the value, it is 13. That I will be obtaining using this. Okay. Ith bit into 2 to the power I. So this is nothing but, this part is nothing but decimal, binary to decimal conversion, the numerator. And the denominator, what does it say? What could be the maximum value for that using those many number of bits, 2 to the power n minus 1. So 13, and if I use 5 bits, so it's 31, 2 to the power 5 minus 1, 32 minus 1, 31. So 13 by 31, this value gives me an idea between 0 to 1, always. This is always, this value will always be within the range 0 to 1. Now, this is nothing but the first quotient and the multiplicative part, these two are nothing but translates me from a number, from a value 0 to 1 to the desired range of the parameter. Okay, so this acts as a translation. That's all. Okay, so likewise for categorical value representation also, the value is found by consulting the range of the parameter. The next is so we were having a set of solutions for population, and we know now we have extracted the parameter value of each and every component of it. Now, how do I evaluate each and every member of the population? That is the task, next task. So, we should have one particular performance measuring criteria to find out how good that particular member is. Okay. So, this process, evaluation process, is a measure of chromosomes performance. So, that means I have to find out a suitable objective function to, select the better fitted ones. Now, how do I formulate the suitable objective function? This objective function should be formulated in a way so that highly fitted members, highly fitted individuals should map to higher fitness values, and similarly lower fitted individuals should also map to lower fitness values. That means I should set a question paper in a way so that good students should get good marks. Similarly, I should set the question in a way so that lower category students should also get more marks. Otherwise, I could become popular teacher but not a good evaluator.
Now this would be a knowledge based learning. You already had some knowledge for the students. So first, you have to take in the class, right? So you don't know who is better and who is poor. So how will you define the fitness?
No, I do not know who is better and who is poor. That is what I am trying to find out. But my question paper should be set in a way so that good students should get good marks. That I can understand from the responses or something like that, from some previous knowledge. Obviously. Some fitness criteria. So that's what I'm saying is that this evaluation function or objective function or fitness function should be formulated in a way so that more suitable strings should get high fitness values. If I set a question paper something like that all students are getting 100 out of 100, then how do I select 50 among them? There is no option for me. Okay. So note that for some problems, this evaluation function will not be stated in a proper manner. We have to formulate on our own depending on the problem itself. Okay. Say for example, fx equal to x square, I know the evaluation function will be x square only. Okay. To maximize fx equal to x square, or on the contrary, to minimize fx equal to x square, it will be minus of x square or 1 upon fx or minus of fx. Both the thing will meet my goal. Okay. So then this selection process should be operated in a way so that it gives more chance to better fitted ones, just to mimic the concept of terminal survival of the fittest strategy. What does this strategy say? This says that highly fitted chromosomes will produce more number of copies into the next generation, will on average produce more number of copies at the next generation at the expense of lower fitted ones. So it should mimic the natural selection procedures. Now, there are different popular selection techniques exist in literature. For example, rounded-cliff process, linear normalization selection, two-numeric selection, stochastic universal sampling. But these are the variation of one among them. All all this selection process should take into consideration the proportionality concept. If the fitness value is higher, more number of copies should be, should be copied. If the fitness value of load is lower, then lesser number. Okay. So let us just try to concentrate on the first one, roulette wheel selection process. What it is? It's nothing but, we can consider it as a pie chart. So I have 5 chromosomes, 1, 2, 3, 4, 5. The segments, amount of segments that will be allocated for each and every chromosome is depending on is in proportion to its fitness value. Higher the fitness value, more area will be allocated to this disk. Okay. So this is the case. What we do is that we try to sum the fitness of all the chromosomes of the populations and call it as total fitness. Then we will generate a random number between 0 to total fitness. So let there be 5 chromosomes with fitness value 20, 10, 40, 7, 14. So the total fitness is 91. We will be generating one random number between 0 to 91. Suppose the random number that has been drawn is 45. Now, depending on the random number, in this particular case, we will try to sum up all the chromosomes. This is 20, this is a line 20, and then 20 plus 10, 30, 30 plus 40, 70, 70 plus 7, 77, likewise. So we have generated one random number between 0 to 91. So it will fall within the range 0 to 91 only. And then we will select that particular segment where the random number is. So in this particular case, the blue colored one, that particular one will be selected. Now what does it represent? Higher the length of this subsegment, more chances that particular segment will be selected. So higher the fitness value, more chances there that particular chromosome will be selected. So in essence, we are taking into consideration the dominant survival of the fittest strategy. Because this strategy says, if the fitness value is higher, I should have more number of copies of it for the next generation. So in this way, we are going to select all the chromosomes.
Here it's not the case because it's not the function of the how high is the fitness value, rather it is the difference between the fitness values.
So it's the first one, second one and third one. So in this case, these particular chromosome will be selected.
Yes, from that this is function of the difference usually, I think, because the difference between the third and the fourth.
Yes, this is function of the difference. This is the difference only. 70 minus 30, 40.
So if the difference is high, then chances
So
of...
this is the way we are basically trying to implement. The concept says something like this. And if we spin the wheel once, and if there is a marker, say some dhamaka, so somewhere it will stop. Where will it stop? More the area, highly likely that particular pointer will stop, will indicate that particular area. So this is the way, this is basically the concept, dominant survival, implementation of dominant survival of the fittest strategy. More is the area. In this particular example, it is highly likely that maybe once or twice this particular segment will be selected, marked by the pointer as compared to this particular segment. So that is what my aim. I should select more number of copies from this chromosome in comparison to this particular chromosome. Because this is weaker, this is fitter. Okay. This particular chromosome should produce more copies for the next generation as compared to this one. So how do I implement? This could be one of the options. That we try to sum up all the individuals, generate one random number between 0 to the total fitness, and it may so happen that the random number could be 72. But the probability is less, because probability of selecting each and every point 21, 22, 23, 24 is 1 upon 1 by 91, right? So for selecting the component between 30 to 70, more chances there, and that is what we are expecting and we want. Understood? Okay. So in this way, if the population contains 5 chromosomes, I will spin the wheel 5 different times, and each and every time the pointer will mark some particular segment, and that segment will be selected. The corresponding chromosome will be selected. So here, this could be one of the ways to implement that particular option.
Actually, what will be the scenario in case of 6 chromosomes? For example, if there were 6 chromosomes and one with the next value of 20, other with 10, third with 40, third with 41. So
both 40 and 41 will have more or less same area. They will have more or less same probability of selecting. It doesn't matter. The concept says that even if the lowest category solution is selected, then what will happen? In the next generation, it may die out due to selection process. Okay, so the chance of selecting lower category, I am not saying that is what I have mentioned, that highly fitted chromosomes on an average. I have mentioned the terms on an average. Highly fitted chromosomes on an average will produce more number of copies. Whatever I am saying that, I am not saying that always the only highly fitted chromosomes will only be selected. It may so happen that sometimes lower fitted chromosomes could have been selected. But once it gets selected, it may die out through the process of selections. Again, in the next generation. Okay, it will not survive.
Then why don't we take this to maximum of the fitness value? Ideally, we're going to fit all these random generations.
Maximum of the fitness value. Then, then that means always 40 will be selected. All the time, if I always select, if the 5 times I select 40, that means the same chromosomes, I will not get anything new out of it. I need no. If I do crossover, it will not generate any new solution, because the decoded structure is same. 00111, all 00111. So if I do crossover,
but it would select the out of 2 out of this, and the rest out of the 2.
that could also have been done. But there is one particular term called premature convergence. It says that if I keep on selecting only the best fitted chromosomes, ultimately I may end up with a solution which is not at all global in nature, global optimum.
Actually, it will be biased.
It will.
Too much of bias.
So we
have to be as much diversified as possible.
Initially, it should have been like that. And later on, over a sequence of generations, if I obtain, and there is one term called homogeneity, and this homogeneity will come, earlier if I have, if the divergence is
actually
less.
you can tell that due to this mutation is
done. But
Because
the mutation probably
bias towards one end to make it reverse.
No, I have not discussed the term mutation yet.
we hope that
We are taking into consideration different types of solutions initially.
globally convergent.
Yes.
Not
If I use all the
You have to cover as much as possible the solution space. It has to be as spread as possible.
diversified. Initially, the diversity should be quite high, and then GA will only lead you to generate one particular
You will make a copy of 40.
Why 40? Because 20 plus 10, 45 comes under into this part.
Means third.
32, 70.
Means third part.
This is the first one. This is the area for first length for first chromosome, the length for second, length for third.
Okay, so you have to take third.
Third, yeah,
Okay,
third
so
one.
I was thinking, for example, at the sixth chromosome with the fitness value of 41, for example.
Yes. Then
So here we will be having one more segment, for example, with color.
yes, 91 plus 45. Sixth chromosome will be
Cumulative sum actually. It is
sixth chromosome will 45, as you were mentioning.
No,
Then
I'm saying 20, 10, 40, then we have one more chromosome with 41. For
Okay.
example.
So 70 plus 100.
No, that will be 71.
70. For up to
Okay.
40 it's 70. Then 70 plus 41, 111.
Okay, so that
111.
interval will be larger than this.
Larger than this one.
You have a larger gene.
Okay, okay.
This is a particular way of selecting.
Way of selecting the seed.
It could
I
be
can have
random.
several other ways that
It could be
are
random, but
mentioned.
convergence will be much larger.
Yes.
You can even give your own.
It depends on, it depends on me only, it depends on the user.
Ma'am, to avoid the biasness, the random selection, initial random selection is.
Yes, to avoid the biasness, right. So if I have 41, then after 70, another part, the fourth part will be 70 to 111.
111.
Okay, then I will generate one random number. If it comes 45, it will select the third one. But if I again, it's not that I will be selecting only one chromosome. If the number of chromosomes in the population is 5, I will do the same procedure for 5 times to get to fill in all the array, all the rows of the matrix. A population is nothing but a matrix. The number of chromosomes, and each chromosome is a concatenation of different parameter values. Okay, so m cross n. So I have to find out 0 to m minus 1. This is the number of chromosomes. So to find out, to fill in 0 to m minus 1, this is the number of rows. I will do the same process for m number of times. Then also the same thing. If I make variable, the variable part will be generated not because of selection part, so maybe due to selection part also, or maybe after crossover mutation also, or maybe after replacement also. In case of replacement part, we will not replace the complete thing by the new one. Maybe some higher category, better fitted 2 or 3 chromosomes will be kept in the population along with the new set. So it depends. So there are several, as I mentioned, that there are several other such selection techniques. Each and every techniques work with certain type of problems, certain kinds of situation. For example, rounded field selection will not work well with close competitive environment, as you were mentioning, one with chromosome 40 and another with chromosome 41. If both the chromosomes are identical, then both are having equal chance of selection. Then if my situation is something like that, I have to select only one, then which one should I choose? Okay, so what could be done is that instead of using rounded field selection process, we could use linear normalization selection. Okay, we will change the original fitness value to some modified ones, and then with this modified version we may execute the rounded field process. So likewise several other selection techniques exist. The next, once the selection process is done, so after selection the selected members are kept into a temporary population called mating pool. Okay. In this mating pool, we do not have any new configuration of the solution, all the old configuration. Some chromosomes are having only single copy, some chromosomes are having more than one copies, and some chromosomes will not have any copy at all. So with this structure, we are now at present will be working with the mating pool only. Okay, on mating pool, we will apply the operators. In case of genetic algorithm, both crossover and mutation are applied, whereas in case of EP or ES, only mutation is applied. Okay, so the first, in case of genetic algorithm, crossover is termed as the primary operator. What it does, it takes 2 chromosomes at a time and swaps some segments. That's all. So exchange of information between a pair of chromosomes with the aim of not losing any important information. But this is our aim. It may so happen that this aim will not be fulfilled. Okay? So exchange of information between a pair of chromosomes. So how do we proceed? Initially, we will choose the partners. Okay, select the mating pairs from the selected chromosomes. Then, say pair number 1 has been selected. So, now as we notice in nature that not all the chromosomes will give me copy for the next generation, but the chance of giving copies for the next generation is quite high. So, we will have one probability associated with this operator called probability of crossover operation. Now in nature we notice that the probability of crossover is quite high. So to mimic the concept of nature, here also we will see that the probability will be kept to a very high value, maybe in the range between 0.6 to 0.9, but not 1 exactly. If I keep it as 1, then all the chromosomes will produce some copies, all the selected chromosomes, obviously. Okay, but that's what we do not want, because in nature also we notice that some of the copies, some of the chromosomes will not give any copy at all. Then check using probability of crossover whether this pair should go for recombination or not. The term recombination in this particular case considers as that whether it should swap its segments or not. So if yes, then only swapping segment will occur. If no, the chromosomes will be kept intact. So depending on number of segments that will be swapped, there are different types of crossovers: 1 point, 2 point, multi-point, uniform crossover, etc. Depending on number of cross sites. Say for example, this is the case of one single point crossover, where only one cross site is present. In this particular case, the 5th one. So the last 3 parts will be swapped for parent 1 and parent 2. We are getting the children.
I have one question regarding the crossover probability. If we have selected a crossover probability that is 0.6 for a particular pair, how can
not for a particular pair. Normally it is fixed beforehand, before executing genetic algorithm. It has been kept to 0.6. So for all the pairs, I will generate one random number between 0 to 1.
Below the 0.6, then it will be selected.
Yes. If it is between 0 to 0.6, it will be selected. Yes. Otherwise no. Yes. It will be selected for segment swapping procedure.
One question. What about the crossover point? Where do we cross over?
Yes, the crossover point is, okay, in this particular case, there is only one cross site.
In this particular case, that means the first 5 bits, they represent first parameter.
No, it's not parameter. It's not parameter wise.
Anywhere between.
Anywhere. Okay. We will use 2 parents. Take 2 parents, produce two children.
So 2 parents.
2 children, not more than that.
Where are the
We have to simplify our life. So depending on number of cross sites, we will have 1 point, 2 point, multi-point. As you have mentioned that Normally multi-point crossover is operated for more than one parameters, where if L1 be the length for first parameter, length of the segments for first parameter, L2 is the length of the segment for second, and L3 for third, then I may select for 3-point crossover, where for first point I will choose a number between 0 to L1. For second point I will choose a number between L1 plus 1 to L2, and for third point I will choose a number between L2 plus 1 to L3, so that all the parameter portion should get modified. Okay, so it depends on me. It has some advantages, some disadvantages also. And single point crossover is advantageous with respect to certain aspect. Multi-point crossover is also advantageous with respect to some other aspects.
Another question. After selecting the chromosome for the applying recombination mutation operator, suppose initially I have 5 chromosomes in the population, and I have used relative selection procedure
Two chromosomes at a time.
5 times. So how can we select the pair of the chromosomes for the
So
recombination?
if normally what we do not take any odd number of chromosomes as number of population. Normally we take given number of chromosomes as the size of the population. Okay. Then suppose 1, 2, 3, 4, 5, 6. So I will generate one random number between 1 to 6 initially. Suppose it's 2. So with the second number should not be 2. It should be x, all the numbers but not 2 itself. So could be 4. So 2 and 4 will be not selected. So these 2 and 4 will be eliminated from the population. It won't be selected again. So I will have 1, 3, 5, 6.
So can I for the selection, can I take all the chromosomes after initial population?
Then you can ask the question afterwards, otherwise you will able to.
Yeah. Okay, yeah. That's it. So likewise we could have 2-point crossover also. Here the cross sites, number of cross sites are 2. So in this case the segments that are swapped is after second, third, fourth, fifth. These many number of bits are swapped. Okay, so we will have 2-point crossovers. I am showing the concept of 2-point crossover. Now, one particular issue that I would like to mention is that such criteria can be visualized in 2 different directions, can be executed. One by using exploitation concept, another by using exploration concept. Exploitation means I will try to find out, I will try to examine all possible solutions for a particular region before moving into another sub-region. This is exploitation. Crossover operator behaves like that. On the contrary, we will see that in mutation it is nothing but a type of drastic change. So here it works with a type of concept of exploration. So this is one of the good feature of genetic algorithms where both exploitation and exploration, these 2 techniques are simultaneously taken into consideration. So mutation works with exploration operator. What it does, it selects one particular bit randomly and negate that bit. So if the value is 0, it will be changed to 1. If it is 1, it will be changed to 0. But for this operator also, some probability is associated. It is called probability of mutation. And in nature we notice that mutation is not, it is not a common event, it's a rare event. So the probability of mutation is kept to a very low value. So this is the case that probability of crossover is kept to a very high value and probability of mutation is kept to a very low value.
It is also possible that if there is a sequence you can make both mutation and crossover together.
Yeah, it is also possible. It's completely random. I am working with, physically I am working with a matrix, and on that matrix we are doing selection, we are doing crossover, we are doing mutation. It may so happen that wherever the crossover was operated, on that particular segment only mutation was also operated. But since the probability of mutation is kept to a very low value, as you can understand that out of, if I keep it to 0.001, then out of 1000 bits, only 1 bit will be mutated. Okay, so it's a rare chance, rare event. But we have some advantages of mutation. It introduces diversity, helps to regain lost genetic material, and the rest part, I think, it's normally the term that I have mentioned is called bit mutation. I will check the probability of each bit with the particular probability of mutation value, and if it exceeds the probability of mutation, then and then only the corresponding bit will be negated. So after crossover and mutation, we are obtaining a new set of solutions, new set of chromosomes. So I was having one old set, now I am having one new set. So as I mentioned that what to do with the old set as well as the new set. So it depends on my replacement criteria. There are mainly two different types of replacement algorithms found out in the literature. One is generational replacement, another one is steady state replacement. In case of generational replacement, all the chromosomes, all the old chromosomes will be deleted to make room for the new set. Okay. So create n children through reproduction, replace the old population with these new individuals. Whereas in nature we notice that it's not discrete, it's continuous, steady state. So in case of steady state replacement, it replaces a few individuals at a time. So we will create M, which is less than capital N, M children through reproduction. So if the size of the population is 30, I will not generate all the 30 children. Rather, I may generate only 10. So these 10, for these 10, I need to find out some rule. Okay. So delete M members of the population to make room for them and insert those into the population. So this is nothing but a continuous procedure. So how long this GA will be continued? It also depends on my choice. I can execute for a fixed number of generations. Okay. Say whatever the marks that I will obtain, I will not read anymore. So this is the case.
In the second case, the deletion will be done randomly.
Which one? This one. Normally it doesn't. We do not do like this. Normally we have some criteria that the weaker candidates will be deleted to make room for new ones. It always something like this. Normally, not randomly. In simple genetic algorithm or conventional genetic algorithm, but I shouldn't say that it was never done. There are some deviation also from this aspect. So execute for a fixed number of generations, or I will execute GA until a string with certain fitness value is located, or until the population attains a certain degree of homogeneity. If the population attains a certain degree of homogeneity, then crossover will not give me anything new, and it is only mutation that can provide me. But since the probability of mutation is very low, it has rare chance to give me new solution, so I can stop. So these are the main criteria for termination. I can choose any one of them depending on my suitability.
In those cases where we just choose a mutation, not the crossover.
Which one?
Like there is segmentation for among the four.
Yeah. In
So
this particular case only we have one after these processes were carried out one after another. Initially crossover is done and then mutation.
No, like for some problem we just use the mutation, not the crossover. For those problems the probability of the mutation is low.
that was not the problem. That was another technique that I mentioned. In evolutionary programming, only mutation is used. In that case, also mutation is normally kept as low, because if you know that this type of heuristic, even if I am using certain heuristics, this is nothing but a kind of guided search. Okay, so through selection, I am trying to find out the better fitted ones. Now, if the probability of mutation is very high, if quite high, then what happens? Whatever I am gaining out of selection, I may destroy the good quality solution, because what mutation does? It negates the bit randomly.
But simultaneously you will not get the
but the theory suggests that if the probability of mutation is greater than 0, you will always converge to a global optimal solution, even if it is 0.0001. Theory suggests that. Okay, maybe the speed is slower. You will definitely get it, but maybe the time to report that, to obtain that particular thing will be quite high. Professor C. Murthy in the morning has mentioned some topic. He has one paper where it was proved that even if the probability of mutation is very low, then also it will reach into the optimal solution. Okay. Now this last part is not mandatory for conventional genetic algorithm. What it does, if I keep on producing solutions using this particular example, sometimes it may so happen that some good quality genes are deleted. So maybe at Tth generation, I obtained one solution whose fitness value was 99. But after that, in T plus 1, T plus 2, T plus 3, I am not obtaining that particular solution, because that solution was died out either due to crossover or due to mutation. But then what to do? This elitist model keeps track of the best solution obtained so far. It's something like finding out the maximum among n numbers. What we do normally, we have another location, max. We keep on taking into consideration one number after another, and if the number is greater than the one that is stored in max, I will exchange that. So this is the concept that we normally do in case of elitism. It keeps track of the base solution that was obtained so far, so that the base solution that was obtained up to Tth generation will not be died out in later part. So this is the whole thing in short. Initialize the population, then compute the fitness values of each and every member of the population. If the termination condition is not satisfied, then selection, crossover and mutation, and replacement. These procedures will be executed one after another until some termination condition is achieved. Okay. This is the typical example that I was mentioning, but note that for this GA is not required to be used. Maximize fx equal to x square, where we are considering, say for example, size of the population is 4, and this is the initial population generated randomly. Fx equal to x square, x lies between 0 to 31, so 5 bits are needed. Okay, so this is the initial population which was generated randomly. So this is the matrix that I was considering. So we will find out its value of x. We will decode each and every value of x. Then my fitness function could be fx only, because maximize fx. So fx is the fitness function. So fi by f bar, that means f average, is the expected count, that how many chromosomes will be, how many copies will be selected for this chromosome. So better is the, higher is the fitness value, better is the chance, more is the chance. So this is the expected count, and this is actual count from rounded wheel. Because if I spin the rounded wheel, either the particular chromosome will be selected or not. So it should always be an integer value. So only the first chromosome will be selected once, so first chromosome is copied once. Second chromosome it has been selected twice, so second chromosome was copied twice. Third chromosome, as you understand, the X value is 4, Fx value is also 4, fitness value is 4. It was not selected, so there is no copy of third chromosome, and fourth chromosome was selected once. So this is the structure at mating pool, temporary population, after selection. Now on it we will apply crossover and mutation. Here I have only shown the crossover part. So for crossover I have to choose the select partners. So suppose 1 and 2 and 3 and 4. So for 1 and 2 suppose the cross type is 4, and for 3 and 4 the cross type is 2. These two numbers are generated randomly. So if the cross type is 4, then only this last bit will be changed. So you see that 0, 1, 1, 0 and then 0, 0, 1, 1, 0 and then 0. Only last bit between first and second chromosome was exchanged. But on the contrary, for this case, first two bits are getting changed. Okay. So X value, and then after crossover, if there is no mutation also, and even if the mutation is there, but since the mutation probability is very low, maybe no bit was mutated, so X value is this one and Fx is this one. Now you can understand that the sum of all the chromosomes in the earlier generation was 1170, and the second generation it is 1754. It has increased a lot, as well as average as well as maximum. But this may not be the case always, because for some generations it may so happen that the good quality genes are died out, and in that case maybe we will, the curve will, it's not that the curve will always increase, sometimes it may decrease, but there is a tendency that it will keep on increasing. So this This is only the second generation. I have executed up to 2. If I execute more than this, maybe I will be obtaining. That I do not know. That depends on the termination criteria. Termination criteria is that there are, I can keep on executing until I get 31. I can keep on it something like this. While preparing for joint entrance examination, what we used to do? We will keep on, appearing different types of mock tests until I obtain 99. This could be the concept of some student, or for some student the concept could be whatever my mom says, I will not read at all. I will read only once. Okay? So there are different criteria that depends on me only. Okay, there are, as I mentioned, that there were 3 criteria, and I mentioned 3 criteria. Okay, so this is the thing that I have shown you for solving function optimization problem. Now the same scenario could easily be solved for different varieties of problem. Say for example classification problem. Here there are 2 different classes of patterns, C1 one set of one class and C2 another class. I have to find out the decision boundary, right? For classification problem, I need to find out a decision boundary only. So any point beyond this value will fall into class C2, and any point within this will come into class C1. So how do I obtain? This is in this particular example, the classes are linearly separable. Let us assume. So in this case, only a line could serve my purpose. So now what is the equation of the line? Ax plus by plus c equal to 0. So if I change the parameters a, b and c, I will get different configuration of the line. Okay? So the thing is that I need to evolve the values of a, b and c in the desired domain. So I can use df. Then what will be my fitness value? Fitness function how do I say that okay, this line is the best one as compared to another line, say it is within it cuts the region C. It's the percentage of classification. I can calculate the percentage of classification. Higher the value, better is the line. Okay. So the same concept, same operators could be used, but in this case the parameters are nothing but A, B and C. Instead of this, if I need to fit a hyperplane, the parameters are, there are 4 parameters. I will involve these 4 parameters, and the classification accuracy, using classification accuracy could be my fitness function. So this is the way that we can modify our representation. The thing is that we have to concentrate on the representational part. How do I represent a chromosome? And then what could be my possible fitness values, fitness function, so that higher category solution should map to high fitness value and lower category ones should lower fitness value.
Can I take piecewise linear functions similarly?
Similarly, this hyperplane is also can be considered as a piecewise linear function also, but many pieces. This is hyperbola. Now, what are the distinguishing characters? How much? 5. What are the distinguishing characteristics of genetic algorithms? The first one I mentioned is that it works with a set of solutions simultaneously, not with a single one. As if you know the term that hill climbing, simulated tunneling, these are also kind of heuristic search procedures. It is a kind of iterative improvement search procedures also. We can also view GA as a kind of iterative improvement search procedure. But in case of hill climbing, it works with a single solution. Here, GA works with a set of solutions. So what is the advantage? If I work with a set of solutions, then that means it has less chance to get stuck to local optima. Okay. So this is more advantageous as compared to the single solution based search techniques. So then it works with on coded parameter set. What is the meaning of coded parameter set? The value x was encoded using some bits, right? So in this case, in that case where x was not an integer quantity, suppose x is a real number. So if I keep on increasing the value, if I keep on increasing the length of encoding x, more and more accurate solution will be obtained. And the point after decimal value, the number after decimal point will be more. Suppose the length of the x is the same example, x is maximize fx equal to x square and x lies between 0 to 31, x is an integer quantity. 5 bits are needed, right? Now if I say for the same problem, x can take any real number, real value. If I use only 5 bits, I will get only integer part, no floating point part. Now if I increase x from 5 to 6, I will get how many?
One decimal point.
After not one decimal point, it's in binary. If on the contrary, if I increase 2 or 3 more bits, then the resolution of the search space will be increased. I will get more and more accurate solution. So it works with a coded parameter set. Resolution of the solutions can be controlled by using the length of encoding the parameter. Then in case of GA, search space may be discontinuous, so which is one of the good property, because if we would have been used the derivative based optimization technique, then if the function was discontinuous in nature, there was no chance to use that particular concept. But whereas GA can use that concept, GA can be used in this category also. Then it uses probabilistic state transition rule. It doesn't require any auxiliary information. Only thing is that a suitable objective function. So based on this, we can execute GA anywhere for solving any problem. Now there are different variations of conventional GAs. It could be distributed GA. Instead of using a single population, more than one subpopulations are used. It could be parallel GA, same GA but with different compute parallel architectures. Then the structured GA, in case of in contrast to linear structure, we can have other structures also. Then hybridization with other strategies and soft computing techniques, maybe neural networks, fuzzy logic. So we would have fuzzy GA, neuro-fuzzy GA, neuro-GA, something like this. So to get better and better quality solutions. So this slide basically provides you a picture, the variety of problems where GA can be executed. Say for example, numerical, combinatorial and constraint optimization problem. The constraint optimization may be the knapsack 01 knapsack problem, where the capacity of the sack should be taken into consideration. Then scheduling, different kinds of scheduling problem, traveling assessment problem, graph coloring. In case of industrial design, biparameterization, routing, genetic programming. In case of classification, I have shown you, but clustering and prediction also, image processing in different tasks, data mining, mathematics, economics, biology, and so on. This list is not at all exhaustive. Only the thing is that if I have to find out the solution of a problem, if I have a problem to solve, that means I have to find out the solution of a problem. Now look at the term find out. Find out means search. So I have to search for the solution of the problem. Now GA is nothing but acts as a kind of search technique. So wherever I have to find out the solution of a problem, I can use GA. Only thing is that we have to formulate a suitable objective function, and how do we represent a chromosome, that is also another issue. It may so happen that whatever I have mentioned is coming under conventional genetic algorithm. But there are several variations exist where the genetic algorithm, the chromosome is not viewed as a binary string. Rather, it is viewed as an ordinal representation. Say for example, traveling salesman problem. In case of traveling salesman problem, we view it as an ordinal number. Okay, that is quite easier. So if I view it as an ordinal number, a chromosome 1 to 10, and a 10-city problem, 1 to 10, any combination, any permutation of 1 to 10 will give me one particular solution. May not be the best one. So in case of traveling salesman problem, say for example, the length of the chromosome is 10 only, and it's not binary string, it's any number between 1 to 10 occurs only once. Each number occurs only once. So if this is the case, then we will see that our crossover operator and mutation operator need to be changed accordingly, so that it will not produce any infeasible solution or illegal chromosome. On the contrary, our concept could be something like that. Even if it produces some illegal chromosomes, we will have some repair version or penalty mechanisms to cope into that situation. Okay. That's all. With this, I would like to conclude my talk.
Any questions?
Enough questions have asked.
Or we can discuss later on. It's a very interesting algorithm. You can apply anywhere, wherever you feel like. These are the references that you can take into consideration. This particular book is very good. The first chapter of, if you just read the first chapter of the book, you will get a good flavor of it. And the example, fx equal to x square, whatever I have shown you, it is there only in this book. And there is one coding part also exists in that book. That is also a good property. How to compute time complexity? It's normally what it says is that this genetic algorithm is normal. You will see that if you see the application part, you will see that the genetic algorithm is used for NP complete problems. but I shouldn't say that for every complete problem, if I use J, I can solve the problem in polynomial amount of time. But what I can say that I will get good quality solution in reasonable amount of time. Okay, but it depends on the each and every part. If I take into consideration each and every component, that how much time will it take for selection, if keeping into consideration M be the size of the population, then it is definitely high, but not as high as an incomplete problem takes. And as I mentioned, is that this is a kind of heuristic search procedure. So it doesn't say that it will always provide you global optimal solution. Okay, always. Sometimes it may provide you global optimal solution, but sometimes it may provide you to near optimal solution, but with reasonable amount of time. So this is what for any heuristic based search technique does. It provides you good quality solution, but by sacrificing optimality and completeness. For any such mechanisms, the performance of any such mechanisms can be evaluated using 4 terms, if we could recall: time complexity, space complexity, completeness, and optimality. So if I use any heuristic search technique, we will reduce time complexity. Time complexity will be lower, but by sacrificing completeness and optimality. Okay. This is always there.